Today, we are going to see another sum on Nyquist stability criterion. Sketch the Nyquist plot for a system with open loop transfer function g of s h of s equal to k multiplied by 1 plus 0.4s multiplied by s plus 1 upon 1 plus 8s multiplied by s minus 1. Determine the range of k for which the system is stable. First of all, we have to get the Nyquist contour. This is the Nyquist contour on S-plane. It goes from 0 plus to j infinity. That segment is called C1. The second segment is called C2. Its radius is R. R tends to infinity. And theta varies from pi by 2 to minus pi by 2. So it is a semicircle of radius infinity. It goes up to minus j infinity. That segment is called C. The next segment is called C3. It goes up to 0 minus. So it consists of three segments, C1, C2, C3. We have to do mapping of this three segments on G of S, H of S, so that we will get a plot on GH plane. That is GH plane. That is called, this axis is called, x-axis is called real part of GH, and y-axis is called imaginary part of GH. Now we have to do the mapping of C1. First, let us do the mapping of C1. To do the mapping of C1, consider what is the C1. What is the value of omega? It varies from 0 plus to infinity. What is G of j omega? GH of j omega equal to k multiplied by 1 plus 0.4 omega j 0.4 omega multiplied by 1 plus j omega upon 1 plus j 8 omega multiplied by minus 1 plus j omega. What is modulus of GH of j omega? That is equal to k square root of 1 plus 0.16 omega square root of 1 plus omega square upon 1 plus 64 omega square multiplied by 1 plus omega square. 1 plus omega square getting cancelled. Therefore, angle of GH of j omega equal to tan inverse of 0.4 omega plus tan inverse of omega. These two for numerator. For denominator, you will get minus tan inverse of 8 omega minus tan inverse of omega by minus 1. Real part is minus 1. Therefore, real part is minus 1. That's why this can be written as, this is in the second quadrant. That's why it can be written as minus of tan inverse 180 minus tan inverse of omega by 1. Now, when omega tends to 0, what you will get here is modulus of GH of j omega equal to k. Angle of GH of j omega equal to, this is 0, this is also 0, this is also 0, this is 180. Therefore, minus 180 degree. When omega tends to infinity, what you will get? GH of j omega equal to, you will get infinity by infinity form. So as a limiting case, you have to find the polynomial and you have to differentiate the numerator denominator with respect to omega. Finally, as a limiting case, you will get 0.05 k. Angle of GH of j omega equal to, for this you will get 90 plus 90, for this plus 90, minus 90, minus 90. Therefore, angle is 0. So if you tabulate all these values from omega equal to 0 to infinity, you will get this table. For intermediate values, if you find for 0.5, you are getting 0.24 angle minus 191. For 1, you are getting 0.13 angle minus 151. For 5, you are getting 0.0559 minus 47. For 10, you are getting 0.05 angle minus 24. These are all you are getting by substituting the magnitude of omega equal to 0.5, 1, 5, 10, and 100. These are the values you got. You notice that initially it is goes above 180. That's why it goes above negative real axis and then come down negative real axis. That's why the approximate plot is looking like this. The approximate plot is looking like this. So the initial value is k 180, that is minus k. After that, angle increases. That's why it goes up. Then angle decreases. Finally, angle comes to 0, that is 0.05 k. Now, this is mapping of C1. Here, we have to find this point of intersection with the real axis. To find this point of intersection with the real axis, what we have to do is, we have to equate the imaginary part of GH of j omega equal to 0. That is, if you multiply the complex conjugate of denominator with numerator and denominator, you will get 1 plus 64 omega square, and multiplying the numerator and denominator by complex conjugate of denominator, 1 plus omega square, and numerator you are getting k multiplied by minus 1 minus 17.4 omega square plus 3.2 omega power 4 plus j 5.6 omega and minus j 14 omega cube. So these two are imaginary parts. These two are imaginary parts with k. Therefore, imaginary part of g of gh of j omega equal to 5.6 omega minus 14 omega cube multiplied. This is the imaginary part. We have to equate this to 0. Therefore, omega multiplied by 5.6 minus 14 omega square equal to 0, or omega equal to 0, 0.632. These are the two values we are getting. For this value, we have to find modulus of g of gh of j omega when omega equal to 0.632. That is, if you substitute on this modulus of g of j omega here, if you substitute here, what you will get is 0.2k. You are getting 0.2k. Therefore, the point of intersection with the real axis, this point is 0.2k. Now we have to do the mapping for C2, mapping of C2. Mapping of C2 is omega equal to r e power j theta r tends to infinity, and theta varies from pi by 2 to minus pi by 2. For this, what is G? What is G of j omega, h of j omega equal to what you will get? Substitute r e power j theta omega. So k 1 plus j 0.4 omega equal to r e power j theta, and 1 plus j r e power j theta upon 1 plus 8j r e power j theta, and 1 plus minus 1 plus j r e power j theta. If we take r e power j theta outside, g h of j omega equal to r square e power j 2 theta, you will get outside r square e power j 2 theta, and here you will get 1 plus j 0.4 divided by r e power j theta, 1 by r e power j theta plus j plus j. The denominator 1 by r e power j theta plus j8, 1 by r e power j theta plus j minus 1 by r e power j theta plus j. That's all. So r tends to infinity means these are all become 0. R tends to infinity means these are all become 0. Therefore, gh of j omega equal to this r e power j theta also getting cancelled. Therefore, finally you will get j 0.4 multiplied by j upon j8 multiplied by j. All j getting cancelled. Therefore, you are getting 0.4 divided by 8. In addition, you are having k. In addition, you are having k. That is equal to 0.05 k. So, the mapping of C2 is nothing but a point at 0.02 k with that's all. Therefore, the mapping of C2 is a point at 0.05 k. That's all. Now we have to find the mapping of C3. That is omega varies from minus infinity to 0 minus. For that, it is a mirror image of mapping of mirror image of mapping of C1. That's why it is nothing but the mapping is mirror image of mapping of C1 means it will be like this. That's all. So it goes this way, then it stays here for omega equal to infinity, and then it returns like this. That's all. So now we have to discuss the stability of the system. So this is the mapping. There are three possibilities. One is the minus one may be here, or the minus one may be here, or the minus one may be here. There are three possibilities. When minus one will be here, the case one is minus one will be there if k is between 0 and 1. Case 1. In that case, if k is lies in between 0 and 1 means this point, this minus k will move between 0 to minus 1. In that case, for this range of k, the system is n equal to what? N equal to 0. No encirclement with -1. What is P in this case? In this case, P is one pole is on the right hand side. Therefore, number of poles on the right hand side, P equal to 1. One pole is on the right hand side. Therefore, P equal to 1, N equal to 0. Therefore, Z equal to P plus N, that is 1 plus 0 equal to 1. One closed loop pole is on right hand side. And the system is unstable. That's all. Case 2. That is second case. That is -1 is not here. It means k is greater than 1. K is greater than 1. K is greater than or equal to 1. And but this point is less than 1. Therefore, what is that point? Greater than 1. 0.2 k equal to 1 means k equal to 1 by 0.2 equal to 5. But k is greater than 1 but less than 5. In that case, -1 is lies in between minus k and minus 0.2 k. -1 will be lies in between minus k and 0.2 k. In that case, n equal to what? N equal to 1 plus 1, because it is in the clockwise direction. And P equal to what? P also equal to 1. Therefore, Z equal to P plus N equal to 1 plus 1 equal to 2. Therefore, 2 closed loop poles on the RHS and system is unstable. Then case 3. Case 3, what it says, if case 3 is, if -1 is here, means 0.2 k is greater than 1. 0.2 k is greater than 1. That is, k is greater than 1 by 0.2, that is equal to 5. Case 3 is -1 is between 0.2 k and origin. So it means the k should be greater than 5, greater than or equal to 5, and less than infinity. In that case, it is the encirclement is in the anti-clockwise direction. Therefore, n equal to -1, but p equal to 1. Therefore, z equal to n plus p, that is equal to -1 plus 1 equal to 0. Therefore, the system is stable for this range of k. That's all. That's all about this.